Okay, so this is going to be a video solution to the capacitor and exponential change problem that I posted yesterday. I think this is a pretty difficult problem, but I like it because it covers pretty much everything, or quite a lot of what we need to know about capacitance and exponential change. So it's a really good kind of summation of the unit. So I'm going to go over this in hopefully a lot of detail to try to cover all of those points. Okay, so we have this circuit here with the capacitor in the middle and then two different switches that can be closed. The one on the right is going to connect it to a battery, and so it will charge up. And then the one on the left, once we disconnect it and it's charged up, we can connect S2 and it will discharge across all these resistors. And so the question starts at that point. So it says, we allow the capacitor to charge up, and we're given this plot here on the right of what the current looks like as we first connect it, and then it evolves. But then once it's charged, that S1 is disconnected, S2 is closed, and we're asked what the time constant is in that scenario. Okay, so time constant, we know that tau equals RC, right? So we have, that's too thick. We have tau equals RC. And so what we need to know about this circuit are the value of R and the value of C, the capacitance. Neither of those things are given to us, so we're going to need to do a bit more work. And that's going to come from analyzing the situation of the capacitor charging, where we do have some information. So let's take a step back and look at that. So when the capacitor is charging up, the initial current, so here's what happens to the current. We know it's going to be exponential decay, right? It starts at some initial, that's up here at 5, and then decays down. And we don't see it for the whole entire time it takes to charge up. That's going to take a lot longer. We know this will continue asymptotically towards 0 as the current fades away and the capacitor fills up. But we're given enough to solve the problem. So I'm going to suggest we take a look at the initial current first, right? Because the initial current tells us about the resistance in the circuit. The reason why is when the S1 is first closed, so this circuit is first connected to an uncharged capacitor, our loop rule just contains the battery and the two resistors. The reason being, we know that the delta V across a capacitor is equal to Q over C, so the charge across the capacitance, or negative in this case of charging up, and the charge is 0 to begin with. So there is no delta VC, and our loop rule just ends up being the delta V across the battery. So that's going to be 60 volts. So we just get 60 volts minus the voltage drop across both resistors. So we have minus IR and minus I times 2R for the second resistor over here equals 0. So that's our whole loop rule. Doesn't contain capacitance at all. And we know what current to plug in here because we know that the initial current from our plot is 5 amps. So if I plug in 5 amps there, I get 60 volts minus, so I'll just combine this R and 2R into a single equivalent resistance, which we could have done before, but it's just 3R. So is minus 5 amps times 3R. So that's our loop rule for when the circuit is first closed. And we can easily solve this. So we'll move over the 5 amps times 3R, sorry. We'll move over the 5 amps times 3R to the other side. And then we can divide both sides by 15 amps. So that'll cancel the 5 amps and the 3. And we're left with R equals 4 ohms. Great, so now we solve for R. And so that's going to be each of the individual R's. So this resistor is 4 ohms, this resistor is 4 ohms, so on and so forth. Those are all 4 ohms. So we'll have to find the equivalent resistance there. So I guess why don't we do that now? Let's find the equivalent resistance for this circuit on the left. What we have is, one resistor on top up here that is in series with the battery. So we can ignore the right side of this circuit right now. So we can kind of just look at the left-hand side of this line because S1 is now going to be open. So when we close S2, we have R in series with the capacitor. So it's the current, all of the current is going to go through this R, but then it's going to split up at this little junction here, and some will go this way and some will go this way. And then so the top branch, or the far left branch, I guess, is going to go down through here, through this other resistor, and then back to the closed junction. And then the current that goes through the other branch will just go through this single resistor here. So we have R in parallel with these two other R's. So R in parallel with 2R. And then that whole parallel section is in series with this single resistor R on top. And so the equivalent resistance for this, Req, is just going to be R plus, so this one resistor R in series with two parallel branches, which is going to be 1 over 1 plus R plus 1 over 2R. So this 1 over 1 plus R plus 1 over 2R, or 1 over R plus 1 over 2R, this is just the equivalent resistance of the parallel pieces, and then that's in series with R. So to simplify this, that turns out to 1 over R plus 1 over 2R is equal to 3R over 2. So flip that and we get 2 over 3R. And so R plus 2 over 3R equals 5/3 R. So our equivalent resistance is 5/3 R, but we know R is 4 ohms. So we get 5/3 times 4 ohms, or 20 over 3 ohms is the equivalent resistance for that side of the circuit. All right, so now we have the equivalent resistance piece of tau. So again, we're looking for R and C in order to evaluate tau equals RC. So now we need to figure out what C is. So we need to go back to this current versus time plot. And what else can we figure out? So we found the initial current, and we used that for good use. Now we need something that does employ the capacitor. And the other thing that we can read from these graphs is the time constant, right? So how long does this take to evolve will tell us about the value of the capacitance. But I'm going to suggest that instead of using the time constant, which after the elapse of one time constant, we'll get the initial current over E, so 5 over E, that's a really ugly value. So I'm going to say, why don't we just start with the half-life? The half-life is the amount of time it takes for the value to decay to, well, half of its original value. So if we start at 5, the half-life will be however long it takes to evolve to 2.5, or to decay to 2.5, which in this case, if we take 2.5 and trace it over, is 14 seconds. So we know our half-life of this right-hand side of the circuit is 14 seconds. And then from there, we know the relationship between the half-life and the time constant is just the half-life equals ln2 times the time constant. So it's much easier to see the half-life from this graph, and then we can easily turn this into the time constant that we're looking for. So T, and then why don't I denote it here as T charging, for time constant for the charging side, because we are going to have two time constants where the problem is asking us to find the time constant for the discharging case on the left, which we won't know yet. But so solving for the charging time constant, it's just going to be tau C is equal to 14 seconds over ln 2, which is equal to 20.2 seconds. Can you hear from my hesitation here that I'm just reading off the answer key for the calculations? So 20.2 seconds. Okay, great. Now we know that the time constant comes from whatever the equivalent resistance and the capacitance of the circuit are. In particular, the time constant is equal to RC, resistance, equivalent resistance times capacitance. And now we just figured out what the resistance is. We figured out that R is 4 ohms, right? And in this right-hand side of the circuit, we have an equivalent resistance of 3R, just because we have one resistor over here with R, and one over here with 2R. So 3R is going to be 12 ohms. And so I can plug that in and we get 20.2 seconds equals 12 ohms times C. And we can divide by 12 ohms on each side, and we'll find that C is equal to 1.68 farads. So now we found the equivalent resistance of the left-hand side of the circuit, and now we also know the capacitance, because the capacitance doesn't change, right? It's the same capacitor that's hooked up to the right side and the left side, no matter it's charging or discharging. So now all that's left is for us to combine those two pieces. We know that tau D, so we'll call it tau D for discharging, is just equal to Req times C, which is equal to 20 over 3 ohms times 1.68 farads, and we find that that's equal to 11.2 seconds, which is our final answer. So to sum up what we just did here, we were asked about the time constant of the discharging case, and so to do that, we had to analyze the charging case where we actually knew something about the behavior, and the two pieces of information that we grabbed from this graph are the initial value of the current, so the maximum value of the current, which gave us the resistance, and then we found also the half-life and the time constant, which gave us the capacitance. So how did I know that those were the two things I needed to grab from this graph? Well, they're really the only two things you can grab. I mean, there's lots of values here. There's a whole curve that gets traced out. But in these exponential decay problems, the initial value in the case of discharging, or in the case of a value that's decaying to 0, or the final value in the case where something is exponentially approaching something from the bottom, we just need that distance from equilibrium, basically. So what is the height that I'm decaying from or decaying to? And then beyond that, the only other question is how long, what is the time scale of the decay? So what is the time constant, or what is the half-life? And we can see in the equations that we write from these things too, where let's just take a generic one, maybe switch colors, y of t equals y naught times e to the negative t over tau, right? This is the basic, or one of the basic forms of all these exponential decay problems. The only two things that I need to plug in here in order to define the behavior of a system are y naught, so that's the initial value. Here it's I naught, this 5 amps, that was my I naught, and tau, or in this case I found the half-life in order to get tau, but that tells us the time scale of the behavior. Then the only thing left is t, that's the independent variable, that's the thing that changes over time. So those two pieces are really the only thing that define the shape of this curve. And so whenever you see a graph of an exponential, or you're another time maybe you're making one, the two things you need to look out for are the height that you're decaying from or to, and the time scale. And that will be the key to solving the problem. All right, so let's move on to the second part of this question. So part B asks, determine the voltage across the capacitor 5 seconds after the scenario in part A, after switch 1 is open and switch 2 is closed. So during the discharging case, we want to know the voltage drop across the capacitor after 5 seconds. So I'm going to erase some of this so we can make some room here. So again, we're just focusing on the left-hand side of this circuit. And in this case, we have a capacitor that's charged up. So we do need to go over to the right-hand side for a sec, just because we'll see this is the positive side of the battery and this is the negative. So our current in this case is going to flow this way. So on the right-hand side, that would be counterclockwise. And we're going to get a buildup of positive charge on this side of the capacitor and a buildup of negative charge on the other. And so when we discharge it, this charge differential is going to be what's driving the flow. So now looking back to the left-hand side of the circuit, so closing S2 with the full capacitor, what's going to happen is these positive charges are going to flow around the circuit through both branches, right? And they'll come back together and come back to this side of the capacitor and cancel out the excess negative charge that was there until it's completely empty. So we know that our voltage across this capacitor is also related to that. We have had it before, VC equals Q over C. Now this is positive because the capacitor is determining the flow of the current. So in this case, the current is going counterclockwise because the capacitor is charged as it is, and now the capacitor is driving the flow of current. And so the voltage change is positive. My loop rule here is going to be an increase in voltage across the capacitor and then a decrease across the resistors. Whereas in the charging case, the capacitor was oriented opposite the current. So because the battery was there, the current was flowing the other way from the positive side to the negative. Or when you do your loop rule, you're going positive to negative. And so that gives us a negative voltage drop. So anyway, this is all kind of adjacent to the actual answer of this question. I'm just giving a little background here. So we know that the voltage drop is going to decrease because we're starting with a maximum value of current and then decaying away to zero. And so as a result, if Q starts large and decays away to zero, delta V across the capacitor will do the same thing. And so we know we're going to have an exponential that looks kind of like the one on the right, where we have an initial value and it decays asymptotically to zero. So this here would be delta VC, and on this axis we have time. And so that tells me that the form of delta V in time is going to be delta VC equals delta VC naught times e to the negative t over tau. Right? This is the form of that exponential that gives us a decreasing, right? The other one, we also have that one that approaches asymptotically, but that is not what we are looking for. So now that I know the form of the equation, let me go up back to the other page. Now that I know the form of the equation, that is going to be delta VC over time equals delta VC naught times e to the negative t over tau. All I need to do is plug in the values for delta VC and tau that correspond to this circuit. So tau is pretty easy. We already figured that out, right? We know tau is equal to 11.2 seconds. We figured that out before. And now we need to figure out what this initial voltage drop is going to be. So when the circuit is first closed and the capacitor has its maximum charge, what is the voltage drop? Well, we know it's equal to Q over C. So we could go that way, try to figure out what the maximum charge is, but at the end of the day, we're just after the maximum voltage, right? And so what do we know that the maximum voltage of the capacitor is? Well, it's the voltage of the battery, right? When you charge up a capacitor with a battery, the final state, like when it reaches equilibrium, is when there's no more current, right? So there's no more voltage drop across the resistors. And so the voltage change across the battery and the capacitor are equal and opposite. So in the charging case, when switch 1 is closed, the capacitor will charge up to negative 60 volts, so it's oriented opposite the battery. And then when we connect the capacitor across this other circuit, S2, to discharge, that means it's going to start with 60 volts. So I don't need to do any of the math. I just know that this delta VC naught is 60 volts from the battery. So there's my equation. Delta VC over time is equal to 60 volts times e to the negative t over 11.2 seconds. So I know we're asked, so why don't we solve the problem first? It asks us for the voltage across the capacitor 5 seconds after the switch is closed. So I'll just plug in 5 seconds. So delta VC of 5 seconds is equal to 60 volts times e to the negative 5 seconds over 11.2 seconds, which works out to be 38.4 volts. So after 5 seconds, the voltage across the capacitor has decayed away to 38.4 from 60. And so now the problem doesn't ask this, but let's go a step further and plot it, or at least roughly sketch it. So we have time here, delta VC here, and so we know we're starting at 60 volts, right? And we know that after, let's just put 5 seconds here, after 5 seconds, we're down to 38.4 volts. Let's just call that somewhere over there. So let me put a little guider here for me to hit with the curve. So I know I'm going to decay down to there. We also know that my time constant is 11.2 seconds, right? So I can also let's put it maybe here, 11.2 seconds. And just being very rough estimating here, we know after a time constant, we'll really have 60 over E volts left, but that's roughly a third, maybe a little bit more. So it's going to be roughly a third of 60, so we'll just call it 20 volts, even though it's not quite right. And so after 11.2 seconds, we need to have 20 volts, and then we'll just say from there we asymptotically approach zero. So this is just a very rough sketch of what the voltage across the capacitor while it's discharging is going to look like. The graph for charge is going to look very similar. Like we said, charge is also going to, so if we plotted Q over T, Q by T, we also get this exponential decay, but this Q naught here, we would have to solve based on the initial voltage and the capacitance. We could solve for the charge, but it's going to have that same shape.